Alright guys, today's goal. The learner will understand functions and their properties. Okay? What you'll learn about: function, definition and notation, domain and range, continuity, increasing, decreasing, boundedness, local and absolute extrema, also considered minimums, maximums, symmetry, asymptotes, and end behavior. And why? Functions and graph form the basis for understanding the mathematics and applications you will see both in your workplace and in coursework in college. Okay. Mapping. And the bell goes off. But why is A function and B not a function? Well, definition of a function. For every input, there is exactly one output. So look, x2, 1, 1, 1, 1. Here, check, but look at this x1. It has 1, it has 2 outputs. That's what makes it not a function. Of the 3 graphs shown below, which graph is not a function, or which is not the graph of a function? VLT, vertical line test. Draw vertical lines throughout the graphs. See how this one? That means for that 1x value, there's 3 outputs. It failed the vertical line test. So C is not, because of the vertical line test. Now, see these? Those are the x values. That means this window here, that's negative 4.7, that's positive 4.7. That's negative 3.3, positive 3.3. Those are the windows, okay? Those are those numbers. Okay? A graph, set of points xy in the xy plane, defines y as a function of x if and only if no vertical line intersects the graph in more than one point. There's the vertical test. Agreement. Unless we're dealing with a model that necessitates a restricted domain, we will assume the domain of a function is defined by an algebraic expression is the same as the domain of the algebraic expression, the implied domain. For models, we use domain that fits the situation, the relevant domain. You can copy these down out of the book later. Don't worry about that, but just understand, if it's not defined, you have to figure out what the domain is implying. So find the domain. Well, what part of the domain? What's the problem here? There's no restrictions. Well, there is. What can you not take the square root of? A 0. So how do we find the domain? Set what's underneath equal to 0 and solve. So you know that x has to be greater than negative 2. So how do we write that? The domain. Negative 2 to positive infinity. So this symbol means can equal. This symbol means cannot equal. Okay? So there's the domain. There we go. Find the range of the function. So think about this. Range, all the possible y values or function values. Well, the domain would be x cannot equal 0. So guess what? If x can't equal 0, guess what else can't equal 0? Y. So let's take a look. So there's the graph. So when you're finding the range, it's easiest to graph. This window, remember, it goes -5 to 5, -3 to 3. So if you look here, these lines should be here right now. Those are the asymptotes. So what it means is it's never going to cross that. So see down here how it has, down here, how it has -infinity to 0, union 0 to infinity. What that means is, remember, these mean cannot equal. So it goes anywhere from -infinity to 0, union 0 to infinity. So that's telling you the only value it can equal is 0. Okay? So these are quick, but hopefully you're keeping up. Okay. Continuity, meaning does it continue? So I'm looking at this graph. I'm following it along. Is at any point did I stop? So it is continuous. Here, oh, one little point there. That means it's removable discontinuity. Okay. Going through again. What's that? Removable discontinuity. Let's slide this up just a little bit. Now jump discontinuity. See, it doesn't equal there, and then you jump up and it does, so there. The domain and range doesn't change, but there is a point that it jumps up where it's not continuous. And then infinite discontinuity is when you have the vertical or horizontal asymptotes involved. Okay? So those are the types of continuity and discontinuity. So let's take a look. Which of the following figures shows functions that are discontinuous as x equals 2? So this is what I do. I go to where does x equal 2? So the x values go from -5 to +5, so 1, 2. So I just look right here. Could x equal, did x have a value there at 2? And how about here? Oh, see how at 2 it goes through that? What's that called again? So this one is discontinuous, and what's that called? The function on the right is not defined x equals 2, cannot be continuous. It is removable discontinuity because it's just one point you remove and it would be continuous. Okay? Increasing, decreasing. So we read graphs just like we read a book, guys. That's the key, left to right. So if I look here, and I'm following, see how I'm getting larger, I'm increasing, I'm moving up. And here from left to right I go down and I'm getting smaller. So increasing, decreasing. This is constant because it never changes. So now, let's take a look here at this last one. See these intervals they have? Left to right, I'm moving down. So that's decreasing from -infinity to -2. It's constant from -2 to 2. And from 2 to infinity, it is increasing. So those are the differences reading graphs. Here's some definitions. Just go ahead, press pause, copy them down, know them. Example, analyzing a function behavior increasing or decreasing. Tell which intervals g of x is increasing and the intervals in which it's decreasing. So let's okay. So if we look left to right, it's going up. So it's increasing from -infinity to 1. But notice, it can't equal 1 because when you see that space there, it means that is going on. And same here. And it's to -1, not +1. That was my fault. Okay? And then it's also still increasing from 1 to 0. Or -1 to 0. And then it decreases from 0 to +1 and 1 to positive infinity. Okay? A local max of a function. So local maximum means there is a maximum there, but it might not be the maximum value overall. So you'll see. And absolute max means it's the largest number you're ever going to see on that graph. And same thing with min. These are called extrema, and they're also called relative extrema. Okay? So make sure you copy this down and you read through these. Example, identify the local extrema. Find the local max or local min. Find the values of x where the local max and local min occurs. Okay. So, I look at 3 points. 1, 2, 3. So, the graph of the function suggests that there are 2 local minimum values. Use the calculator. So if you don't remember how to find max and mins, I will do so. But here's the thing. This point here is not only just a local min, it's an absolute because it is the minimum of the graph. This is called a local maximum value because you're switching from increasing to decreasing. Okay? And then that's just a local minimum because, yes, you switch again, and it's not. It would be a minimum in this window, but not in this whole window. That's the absolute because it's the smallest minimum value of the whole graph. Okay? Symmetry with respect to the y-axis. Symmetry means if you fold it over a line, they match up. So graphically, if you look at it, if I folded it over the y-axis, they would match. If you look at it here, see how 3 is 9, -3 is 9, -2, 4, 2. It's the same distances. Okay? Now, this is very key. F of -x equals f of x. You see how when x was -3 it equaled 9, and when it was +3 it equaled 9? So opposites are always equal. Hopefully we remember these. Now, if you haven't had enough time to copy some of these pictures and slides down, do so. Just go back, press pause, copy them down, okay? Symmetry with respect to the x-axis. So before, the opposite x values equaled each other. Now it's the opposite y values equal each other. Except if there's a 0, then that means it's just equal to itself, so. But same thing, just reversed. Okay? Symmetry with respect to the origin. F of x equals negative f of x. So watch what that means. X is -3. So if I plug that in, I get -27. Now, that should equal negative times f of x. Oh, hold on. I got to back up here. The negative was inside. So really, this should have been f of -3, like that, equals, well, that would be 3 to the third, so 27. And then negative f of -3 equals negative, which is negative times -27, which is still 27. Okay? So you know two things are symmetrical for odd functions around the origin when that is true. Even functions can't, so it's got to be odd. Okay? So make sure you press pause, copy these down. We'll talk about the limits here. Tell whether the function is odd, even, or neither. So, odd, even, or neither. You can't tell just by the exponent. You got to check. Remember, if it was odd, that would be, you could have it about the origin, or if it's even, it's about the y-axis. So, look at the graph of it, and just come in with this answer tomorrow.